attending our Rigid Flex Gerber Layout Guidelines and Requirements webinar. My name is Kendall Paradise. I'm the president at EPIC. Before we get started today, I just want to let you all know that you will be muted during the presentation. If you have any questions as we move along, please enter them in the questions panel located in the webinar control panel. Also, we will be recording this live webinar and we will be posting both the recording and the slides on our website and YouTube channel. Our presenter today is Paul Tomei, our product manager for Flex and Rigid Flex printed circuit boards. Paul oversees our entire Flex and Rigid Flex product lines. His main responsibility is customer technical support. However, he's involved with each product from beginning conceptual stages to delivery. He works directly with our customers on specific design requirements and makes sure that each product is designed correctly, troubleshooting with any issues that may arise throughout the manufacturing process. Paul came to EPIC with over 25 years of experience across the entire industry, including sales, engineering, and manufacturing. Previously, he was the president of Advanced Circuit Services, and his experience and expertise make him an indispensable part of our team. So I will turn it over to Paul and let him start the presentation.
Well, thanks again for joining us today, everyone. We appreciate your attendance. As Kendall mentioned, today's topic is an introduction into some of the unique elements that come into play with rigid flex designs from at the Gerber stage that aren't present or part of your traditional rigid board design process. Wanted to start off by, excuse me. There we go. Sorry about that. So a couple of the more specific and more important elements that a rigid flex design introduces into the layout phase revolve around the presence of rigid to flex transition lines. There are also some elements related to the layer stack-ups and also a couple of items that pertain specifically to the trace layout within the flexible areas of the design. Wanted to start off by identifying that all of the items that we're going to cover today in this presentation adhere to IPC 2223C recommended rigid flex constructions. IPC 2223C is a standard pertaining to specifically flex and rigid flex designs. By adhering to 2223C, the design it will ensure that the design achieves the highest degree of reliability and performance possible. And from the image that you see below, a few of the key elements are first, the use of an adhesiveless flex core. Secondly, a selective flex area coverlay design where the coverlays exist only on the flex areas and do not extend within the rigid areas. And then the use of a no-flow prepreg to achieve your layer lamination within the respective rigid areas. So moving on to the first item. And this is definitely the most unique element and, in my opinion, the most important element. And that is the rigid to flex transition lines, or in other words, where the flex extends out from within the rigid areas and becomes visible and then extends over to however many other rigid areas exist. The special requirements, again, pertain back to IPC's 2223 standard and also to some of the unique manufacturing methods that apply in the construction of a rigid flex. And one of the most significant one is that in the most common manufacturing method, the rigid material that would normally exist in the rigid areas is actually removed from all of the layers prior to the actual layer lamination process. So as we move on, I think some of this will become a little clearer. So the first element in the layout, or the first element in the Gerber layout that needs to be conformed to is the spacing from plated through holes, be them either PTH or component holes, as measured to the rigid to flex transition line. And this is an important element in maintaining this 50 thou minimum requirement to ensure that the vias are not being drilled through the cover lay that will engage the rigid areas by a small amount. This spacing accounts for accumulation of all of the various manufacturing and material tolerances that are present in the process. And by eliminating the vias from being drilled through the cover lay, dramatically improves the reliability of those vias. The second item pertains to the external layers and the copper features that exist on the external layers. In this case here, a minimum spacing of a copper feature to the rigid to flex transition line of 25 thou minimum allows for the manufacturing methods and tolerances during the specific outer layer imaging processes only. And again, specifically, this is being driven by the fact that the rigid materials have been removed and do not exist during this process step in the flexible areas. Moving on into layer stack-ups, a few items. First and foremost is the thickness of the flex cores that are used. And as a standard rule, the thinnest layers practically possible are recommended. And in turn, this improves the flexibility of the flex areas, which in turn improves the mechanical reliability of them. And as an extension of that, allows much tighter bend radiuses to be achieved reliably. In most cases, we recommend a 1 thou core. Impedance control designs, in order to achieve the impedance values, will require thicker cores, and those typically will increase into the 2 to 3 thou range, depending upon the specific requirements. Another important item is achieving a balanced construction with the flex layers centrally located within the stack-up of the part. And what this prevents is any potential warp and twist in the finished assembly arrays. There are some potential cost adders that can come into play if it's an unbalanced design. Unbalanced designs are possible, but we always recommend that you review your construction with your supplier in advance to ensure that you understand the ramifications and the limitations or any potential limitations that might exist. As you can see from the two images below, which are both based on a 3-layer construction, the leftmost being a balanced one where the flex cores are located exactly in the center of the stack-up, and an unbalanced one where the flex core has been moved up to the top. As I mentioned, both are indeed doable. A balanced construction is always preferred. A few other elements, and this is fairly important. It is strongly recommended that all of the rigid areas within the design have the same finished thickness. If a thickness variation is required, then you're looking at some very complicated sequential lamination processes, which in turn bring along some significant added costs. And again, this is an item that we strongly recommend that you consult with your supplier to determine the viability of it prior to moving forward with the design. A very common question that we get from many of our customers is layer counts. And as with flex, in rigid flex, odd layer counts are indeed allowed and very, very common. You know, a 5-layer rigid section with either 1 or 3 layers of flex is a very common configuration. The number of layers within the flex area, we always suggest to our customers that the layer count be minimized to in turn allow for the thinnest possible construction. This in turn improves the flexibility, improves the reliability, and improves the bend radius capability. And regarding copper weight, by far the most common copper weight used in flex and rigid flex is ½ ounce, and that is indeed what we recommend. Again, by minimizing the copper, which is the stiffest component within a flex construction, the flexibility and the mechanical reliability is improved, and also in many cases facilitates impedance-controlled circuits and achieving those values. 1 ounce copper is available, is used fairly often, but it's typically reserved for applications that have a higher current carrying requirement that can't be accommodated with ½ ounce. Another element in the flex structure is dealing with the flex layers as pairs rather than a solid stack of layers. In the two examples that we have here, one is an 8-layer with 2 layers of flex. The other is an 8-layer with 4 layers of flex. But as you can see in that example, the 4 layers are configured into 2 pairs of 2, which are not laminated together. This allows the design to adhere to IPC standards. Again, improves the flex area, flexibility, and mechanical reliability, and is definitely the preferred structure. Having said that, not all designs will allow that, and specifically we encounter this on impedance-controlled or designs that require shielding in the flex area. And in most cases, it requires either 3 or more flex layers to be bonded together to meet the ultimate design requirements of the specific part. In these designs, it's very important to use a layer structure that minimizes the amount of adhesives used to bond the flex layers together, which in turn allows the design to best conform to IPC standards and provide the highest degree of reliability. Bonding the layers together, specifically when you get up into the 4 or 5 layer count range, does have a potential negative impact on the flexibility and the bend requirements, and that is something that should be investigated and understood completely as early on as possible in the design process. We strongly suggest that you consult with your supplier for the best possible configuration for these types of applications. Moving on to some trace layout guidelines, specifically in the flexible areas. We always recommend to our customers that traces be offset from one another as you look at the end of the design from layer to layer, if at all possible. And you can see in the first image there, the preferred, where the traces, this is an end view of the circuitry, where the traces are offset from one another. This has a positive impact on the mechanical flexibility of the design by eliminating what's referred to as an I-beam effect. And again, it's a piece of cheap insurance. If it's possible, we definitely suggest that it be done. As you can see in the not recommended image there, where the traces line up from one another, it will constrict, it will stiffen the flex areas, which in turn restricts the flexibility and could, under extreme situations, create reliability issues. In an impedance control design, primarily due to the requirement of a solid reference plane as one of the layers within the flex areas, not possible, but we still suggest an offset. In this specific case, there's layers 3 and 5 are impedance controlled. Layers 4 is the reference plane. So achieving that offset does improve the flexibility to a small degree, definitely worth considering and implementing if possible. Another significant element is the configuration of the traces in the flex area. The standard recommendation is that the traces be run in a straight line from one rigid area to another, parallel to one another, without any changes in direction, if at all possible. And by doing so, you eliminate any potential mechanical stress concentrators that would be created in these bend areas. Now, not all designs will allow for that, so if a change in direction is required, then we definitely recommend that the trace corners be configured in a rounded shape or configuration, if at all possible. Utilizing 45 degrees is allowed. Using 90 degrees is definitely not recommended.
Thank you, Paul. While Paul was reviewing your questions from his presentation, I would just like to take a minute to introduce everyone to EPIC's other product lines if you aren't already familiar with them. EPIC focuses our business on build-to-print products such as battery packs, user interfaces, fans and motors, cable assemblies, as well as rigid printed circuit boards. Paul, the next slide, please. For each of these product lines, we have dedicated product managers as well as design centers and technical support centers for the various lines across the world, located locally here in New Bedford, as far away as Southeast Asia. So looking at our different product lines for our battery and power management is in Denver, Colorado. Our user interface facility is in Largo, Florida. For fans and motors, we're based out of Wales in the UK. Our rigid printed circuit boards are here in New Bedford, Massachusetts, and Shenzhen, China. For flex and rigid flex in Toronto. And for our cable assemblies here in New Bedford, Massachusetts. Our product managers are always willing to work with customers from concept through to the end of production. Paul, I'll turn it back over to you to handle any questions.
Well, we had two questions come in. We've had a few questions come in, probably the two most relevant ones. First, the question is, are vias allowed within the flex areas? And the answer to that is yes, they are, but it's not a preferred situation due to the mechanical stress concentrators that the vias create, which in turn could create reliability issues. And also from a cost perspective, in that having vias in the flex layers, or in the flexible areas, creates essentially a blind via or buried via structure in the manufacturing process of the part. It's doable. There are cost factors. Again, an element that we suggest that you consult with your supplier in advance so that you understand the implications before you move forward. Second question that we received today is, are different layer counts or different flex layer counts allowed between different sections, between different rigid sections? And the answer to that is yes, it is. It's fairly common. There are some details that may come into play. You know, we've manufactured many designs that would have 2 flex layers from, say, rigid section 1 to 2, and then 3 flex layers from sections 3 to 4, or section 2 to 3, I should say. So it is possible, not very common. It is definitely worth considering due to some improvements that can be had in the mechanical bending and reliability elements of the design. Again, we suggest that you discuss this with your supplier in advance, early on in the design process, so that you understand the requirements and the any potential ramifications. And with that, we'd like to thank you for your attendance today. It's been a pleasure, and feel free to email